So welcome. I'm talking about scalable time series and stream processing for IoT applications today. Now, as you know, Internet of Things, bit of a motivation there. There are many different areas why it's worth it to look into that stream processing, time series processing. One of them is the aviation industry, airlines. One of the legs, typical A380 does, produces terabytes of data. And if you can take that data and increase the precision of the ETA, you can shave off millions of dollars per flight. With logistics, it's pretty much the same. The sensors that are on the ships and trucks and so on and so forth allow you to realize a number of really interesting business use cases. And healthcare being another example, be it self-service, be it patient monitoring, many different domains. There are a lot of sensors and they typically produce a lot of data, which is typically time-stamped. Traders, online trading, high-frequency trading, another area where not physical sensors, but a lot of sensors, a lot of sources, let's say, produce a lot of timestamp data. The farmers, they have a lot of data there in their daily routine, and again, they're the same motivation to optimize the way how things are done. Smart cities, anything from flow control over parking, optimizing the ways how the city is used. And last but not least, if you think about smartwatches or even smart jacket, be it your fridge or something else in your home, like the heating. So all of that essentially requires us to process a lot of data from various physical, virtual sensors, and that typically in a time-stamped manner. So first, let me talk about what I call the toolbox. A toolbox essentially being a number of technologies, a set of technologies that I've divided into 3 buckets. And we will later on see how those play together. But first, let's talk about workloads a bit. If you look at any given system out there, you will find this range of the spectrum of workloads from batch systems over stream processing systems to PAS level stateless things. And we're going to talk about the middle part there. So one bucket or one category in my tool belt, in my toolbox, are so-called message queues and routers. A couple of examples: Apache Kafka, CRMQ, RabbitMQ. There's recently a Redis-based queue called Disk. There's FluentD, Logstash, Flume, Akka Streams, and there are a couple of cloud-only offerings, AWS SQS or Google's Cloud PubSub. And there is actually a very nice website called queues.io that compares these different offerings, and we're going to have a look at 2 of them in greater detail in a moment. First of what we're going to look at is Apache Kafka. Originates from LinkedIn together with SAMSA. Essentially, the use case they have there is pretty much what it is used as well, mainly today. Decoupling producers and consumers. So you want to have a very loose coupling, want to be able to add consumers and producers independently. And the interesting thing about Kafka is that it is persistent message queue, so it writes its data to a disk very fast, high throughput. It's distributed, so you can have multiple brokers there, very reliable, and number one component in any large-scale IoT stream processing setup, I would argue. Another one I've picked there for different reasons fluently. And fluently, if you look at that, again, left-hand side being the publishers, producers of information or messages, right-hand side being the consumers, it looks pretty similar. What I find interesting there are its routing capabilities, so that you essentially can come up with rules, and based on that, on these rules, you can say that certain messages, for example, are routed from a certain front end to, let's say, an analytics backend like Hadoop. The second bucket or second part, so once we have the data queued up and made available, is the actual stream processing itself. Again, a number of open source components and frameworks out there, such as Apache Storm, which has been around arguably the longest. Apache Spark, Apache Sams, already earlier mentioned, has been developed together with Kafka. Apache Flink, a rather new addition to the mix, Concord, and again, there are cloud-only offerings like AWS Kinesis and Google's Cloud Dataflow. I have another webinar on stream processing, comparing a couple of these options in greater detail. And again, let's have a quick look at two of them. Apache Storm, as already mentioned, has been around the longest, for a couple of years now. It is, again, a distributed system, a distributed fault-tolerant stream processing platform. And what you're essentially doing there is you're defining a so-called topology programmatically, so in Java, for example, that has certain so-called spouts, which are the sources of streams, and so-called bolts, which are essentially the compute units, and you have a wiring between that. On the right-hand side, you see such an example, and all these spouts and bolts together make up a topology. It is a very flexible and a very low latency solution. So with Storm, you can easily process streaming or have streaming applications that react in the milliseconds range, no issue at all. On the other hand, we have Apache Spark, a very popular solution that has as a number one advantage, at least in my experience, that it allows you to do batch and stream. The streaming there is essentially micro batching, so you can use it down to maybe a second, half a second, reliably. Certainly not as low latency as Storm, but the powerful thing is that you can combine it with a lot of other things. So you have this core abstraction of a resilient distributed dataset, RDD, and then you have multiple APIs on top of that, Spark SQL, streaming, machine learning library called MLlib, GraphX for graph processing, and Spark can execute in different cluster modes, Mesos, standalone, built-in, and Yarn. And with Spark, you have, as I said, a kind of universal processing platform where you can, if you think in terms of Lambda architecture, for example, do both the online part and the speed layer and the batch layer. Let's move on to something more specific, time series processing. That is quite a range that starts with how to store time series values to how to visualize them, how to interact with them. Hence, you can expect anything from time series databases to more on the interaction and visualization end. And I have a advocacy website around that topic. And there are certainly some contenders there. We're going to have a look at, again, two of them. OpenTSDB, which operates on top of HBase, so it's a distributed system, natively distributed. You can, it's very powerful. You can process and store a lot of data with it. It is very scalable. It's really, HBase, based on HBase, and through that you can have billions and billions of time series events in there. Typical use case are things like monitoring. If you have, for example, a MySQL server farm or whatever, you want to see how all of the machines are doing. That's one of the canonical use cases for it. On the other hand, we have InfluxDB, which is a very, very powerful standalone but also distributed time series database that provides for a SQL-ish query language that even if you're not that familiar with SQL, you will appreciate, rather than having to put together your queries yourself through the HTTP API. You can, in a very expressive way, state your queries there. The distributed mode that is based on the Raft algorithm is another option. It's certainly not as scalable as OpenTSDB, but has a number of very nice integration points, for example, with Grafana, and very, very simple to set up, especially in the Dockerized environment. Okay, so if you look at all these different components, and for any given application, you might pick one or more of each of these categories and put them together in a data pipeline. You will find a number of challenges, and I will, in the following, not going to talk too much about the challenges from the application development side, like how complex is it to write a storm topology, or how to write an application in Spark or whatever. I'm talking about now if you're building such a system, how would you actually operate that and get the most out of it. So on the one hand, there is a certain cost and effort that comes along with setting up and operating these different components. In contrast to, let's say, a relational database where you have one system for all kinds of things you have seen, here we have quite some moving parts, if you wish. So you will have to learn how to install and operate each of these components. Second is what is generally called elasticity. And that is basically boils down to, especially if you have distributed systems, you typically have dedicated clusters for certain things. So you might have a Kafka cluster here, and a Spark cluster there, Storm cluster there, and so on and so forth. Now, if you want to change something, if you want to say, I need more compute power in the Kafka cluster, for example, then you need to manually provision the machines, take it, let's say, from somewhere spare or from the Spark cluster or somewhere else, and add them to the Kafka cluster. And that is, it takes a bit of time, and it's not as elastic as if you could just say, okay, I need more compute power, or more storage, or whatever, and just by flipping a switch, essentially deciding where the compute power should go. Last but not least, it's a matter of how efficient you're using your resources. So if you think about CPU utilization, memory, typically in industry standard, you would see anywhere between 10 and 20% utilization. Why is that so? Well, because you're provisioning, you're over-provisioning, you're provisioning for the maximum load, but 80-90% of the time, you will not see this maximum load only at certain events or at certain times. So most of the time, you have slack resources, you have resources you're paying for, but not really getting any value out of it. So these three things taken together are a motivation to present something or suggest something that addresses all three of them. And that is the so-called data center operating system. One way to understand the data center operating system is if you compare it with a local operating system, if you wish. The data center operating system, DCOS, is really a distributed operating system. So it operates on the number of different machines that build or represent a cluster. And in the same way as you have certain subsystems or certain functionality in a local operating system, let's say Ubuntu or Red Hat, CentOS, whatever, you have a Linux kernel. In the data center operating system, this functionality or this subsystem is Apache Mesos, and so on and so forth. So for each of these things, be it memory, be it networking, and so on and so forth, you will find an equivalent component, equivalent subsystem in a distributed operating system, such as the data center operating system. And there is a bit.ly link down there if you want to look that up later on. So as I said, the DCOS is a distributed operating system. It assumes a cluster of machines that can be, bare metal, that can be virtual machines, and it has on each of these machines a so-called local operating system running. That could be CoreOS, something very lightweight and container native, or it could be Red Hat or Ubuntu, whatever. It provides for different number or different kind of workloads to be scheduled there, long-lived things, like, for example, a web server, whatever, batch workloads, and so on. You have networking, service discovery, especially if you're talking about, containerized workloads. You have stateful services, databases, distributed file systems. You have a security component, and then monitoring, logging, debugging, and so on and so forth. So all of that together is what we provide there. And the Mesosphere DCOS essentially allows you to operate on any given existing physical or virtual infrastructure that can be on premises or that can be in the cloud. And it provides these basic core services, as I mentioned earlier on. And the top layer here, you see this ecosystem of services and applications. Some of them already mentioned earlier on, and some of them for other workloads and for other use cases, such as Kubernetes or MongoDB or Jenkins, if you think about developer agility, CI/CD pipelines. Now, what are the benefits if you think of running such a stream processing IoT infrastructure? You can run that together with other stateless services like a web server, application server on the same cluster. You have supports this dynamic partitioning depending on your business needs, and you see an increased utilization. Different applications, different workloads are stacked above each other, and you find up to 80% or even more utilization in such a DCOS cluster. Now let's have a look at an example, a concrete walkthrough example, what we call the time series DCOS demo or crime buster. What we did there, and there's a blog post if you want to read it up, is essentially taking a certain crime database from the Chicago area. It's a XML dump around 600 megabyte. We set up a data processing pipeline using Kafka, which essentially gets these messages one after each other ingested. Each of the messages essentially has a time component, so a timestamp and a geolocation, latitude and longitude, and the most important information, what kind of crime, so robbery or battery or theft or assault or whatever, and then a couple of other information. And that is essentially in this Spark. In the middle, you see the Spark streaming application that has two paths. On the one hand, the upper path, that's the online path, and on the other hand, the lower path, that's the offline path. And the idea is, in the online path, you essentially want to provide an overview of what has happened in the last 5 minutes, 10 minutes, or whatever. So which kind of crimes are currently peaking. So you can, for example, if you think about dispatch, you can, send certain units or activate certain units based on what you see currently. On the other hand, the offline part aggregates all the data from the beginning of time, so from whenever the simulation started, into a heat map and overlays that. And with that, you essentially see hotspots, you see in which areas of the city certain both passes have their use cases and can be driven by the same application. In the upper part, we decided to deploy these different components with Marathon, and in the lower offline part, we decided to deploy that with Kubernetes. And all these different components, Marathon, InfluxDB, Kafka, Spark, Kubernetes, and so on, are deployed as services and applications on the DCOS. Took us less than 2 days to actually do do everything from end to end, from the conceptualization over data sources to implement and deploy and run the actual demo. And this is something that is both in the architectural and actual implementation level, actually scalable. So that could actually already be used in production. You would probably want to introduce some security features or access features around there. But in terms of the data path and the data processing itself, it certainly is production ready. There's just a few impressions there. You see the heat map, the overlay. You see the visualization, the online path Grafana, which is used as an visualization tool in front of InfluxDB, and the DCOS dashboard where you see when everything is running, some 80% utilization. That is exactly what I mentioned earlier on. These different frameworks and different applications stacked upon each other, essentially, utilizing the overall cluster. In our case, we had 5 private nodes and 1 public node, so 1 publicly accessible node running out there. And I think with that, we're already at the end. I'm now happy to take your questions, and a few links at the end. I'm going to share the slide deck right after. So now we got a couple of questions there. Do you know Basho? Yes, I know Basho. The question there in terms of Basho's offering React and how to compare it with InfluxDB. As I said, if you want to have a distributed system and you're looking for something that, in terms of scalability, you're not shying away from setting up a cluster of machines, then anything on top of a distributed system like HBase, Cassandra, as Kairos, and I believe Basho recently introduced a time series database on top of their React offering. Anything in that domain is better than building it yourself. I don't have any hands-on experience with that system. It's, I think, pretty new. So in that sense, InfluxDB has this huge advantage that it has this SQL-ish query language that helps you to very quickly get to express what you want to see. I don't know the interface in React's case or React's time series case. You're welcome. Clarification, is it possible to run DCOS on bare metal? I'm thinking Raspberry Pi. Theoretically, yes. I believe the only requirement coming from Mesos is it must be 64-bit Linux, right? So anything, just pointing it here, who asked that question? As bare metal, as long as it runs 64-bit Linux, should be fine. And I believe, I would need to dig it up, but I believe that someone already tried that, at least Mesos. I'm not entirely sure with DCOS, but Mesos, so our distributed kernel, yeah. Right. Okay. So, yeah, I'll switch off the recording, but I'll stay around on the chat. Okay, thank you guys.